Aloha and welcome to Bundles of Joy, a talk about breaking macOS via subverted application bundles. My name is Patrick Wardle. I am an independent security researcher who focuses on all things related to Mac security. You might be familiar with my Mac security website and tool suite, Objective-C, my Mac security conference, Objective by the C, or the book I'm writing about analyzing Mac malware. So today's talk is a story I wanted to share with you, whose main character is a lovely bug that affected all recent versions of macOS. So the majority of the talk is going to be about analyzing the flaw, reverse engineering the operating system to ultimately uncover the root cause, the reason for the vulnerability. We're also going to talk about some other chapters or interesting aspects of the bug, including the fact that we discovered it in the wild, exploited as 0-day. And then we're going to also talk about some defensive measures, mechanisms, such as ways to detect exploitation attempts, ways to protect the system. And then we're going to end the talk by reverse engineering or analyzing Apple's patch to see how they ultimately closed the door on this vulnerability. So first, let's talk about how Apple protects Mac users from infection, as the bug we're talking about today was able to neatly sidestep many of these protections. First, though, it's important to understand how Mac users generally become infected with malware, computer viruses, Trojans, etc., etc. So the vast majority of these infection vectors require some sort of user assistance. It's very rare to see a pure remote 0-day exploit being used to deploy malware to Mac systems. What is far more common is adversaries or malicious attackers coercing or tricking Mac users essentially into infecting themselves. So on the slide, we have some examples. A lot of times users might be browsing the internet and they come across a site that has malicious advertisements or has perhaps been infected. And this website will display something like a fake update. A very common one on macOS is an alert or a pop-up saying your Flash player is out of date. Please download and install the required update. Of course, this is not a legitimate Flash update, but instead malware. But the user is tricked into downloading and installing what they believe is a required Flash update. They will have inadvertently infected themselves with malware, computer virus, malicious code. Other examples include pirated applications. Ethics aside, a lot of pirated applications contain malicious code, so it's not a good idea to install such applications. But a large number or some number of Mac users, unfortunately, will download and install these applications, looking for popular ones, things like free versions of Photoshop, etc., etc. Again, if the user downloads and runs these, they will become infected. So again, really the main takeaway is the attackers are pushing malicious code, but the user is essentially responsible for infecting themselves by ultimately running the infected application or binary. Now, as Macs become more popular, so too do attacks and user infections. So Apple really had to do something about that. And what we're going to be talking about today are the anti-infection mechanisms that Apple introduced in recent versions of macOS, essentially designed to protect the users from themselves. And so these are mechanisms which we'll talk about, but include file quarantine, Gatekeeper, and Notarization. And again, the aim is really to protect the user from infecting themselves. Now, before we dive in and talk about those protection mechanisms that the operating system provides, which again are important to our talk because the vulnerability we're going to talk about is able to bypass these, we need to understand the quarantine attribute. The quarantine attribute is added to anything that's downloaded from the internet. So if you download an application, if you download an email attachment, you save something from a WhatsApp message that someone has sent you on your computer, the operating system or the application is going to add something called the quarantine attribute. This is an extended attribute. You can examine it with the xadder command if you pop open a terminal. For example, on the slide, we can see that this application I've downloaded has the com.apple.quarantine attribute, and this also has information about where it was downloaded from. The importance of this attribute, as we can see on the slide, is it really signifies or alerts to the operating system that this item should be checked by various anti-infection mechanisms when the user goes to launch that. So it's kind of the catalyst, or rather the trigger, that says, hey, operating system, macOS, please do a gatekeeper check, do a notarization check, do a file quarantine check. So again, the quarantine attribute is very important. So now let's talk about some of the anti-malware, anti-infection mechanisms that Apple has added to recent versions of macOS. Again, the goal here, Apple's goal, was really to protect the user. So even if the user was tricked into downloading something like a fake Flash player update that was actually malware, if they went to run it, the operating system, in theory, would prevent that, and thus, spare the user from infecting themselves. So first up, we have file quarantine. This was added all the way back in 2007. What file quarantine does is simply alert the user that something they are opening is A, from the internet, and B, something that contains malicious code. So if the user double clicks something and it has that quarantine attribute set, which will be set for any downloaded item, they will see a file quarantine alert. This was important because a lot of Mac malware was masquerading as benign file types. So for example, on the slide, we can see Windtail that was being distributed to users with an icon representing Microsoft PowerPoint. So, a user might download this or open it in an email attachment thinking it's a benign PowerPoint presentation. Well, file quarantine will jump in the way and say, hey, just to let you know, this is an item from the internet, and also it is an application. Perhaps not the PowerPoint presentation you are expecting. The problem is the alert had an option to click open, and so users would say, yeah, sure. They wouldn't read the prompt, they wouldn't read the alert, and a lot of them would click open, which would allow the payload to execute, and if it was malware, then the user would become infected nonetheless. So Apple said, okay, hey, we need to introduce something a little more substantial, something to protect the users even more, because unfortunately they are still inadvertently infecting themselves. So in 2012, Apple introduced a technology known as Gatekeeper. Gatekeeper, again, is triggered by the presence of the quarantine attribute. If the user double clicks something that has that attribute set, Gatekeeper will intercept and examine the item. And essentially, it's looking to see if the item has been signed with a legitimate developer ID. Apple's reasoning was that malware wouldn't be signed, whereas legitimate applications would be. But there is a shortcoming, or there was a shortcoming, that once Gatekeeper became popular and widespread, malware authors simply began signing their malware, and thus essentially sidestepping Gatekeeper. One thing to point out, though, that the alert, the Gatekeeper prompt doesn't actually have an option to allow an item to run. So if the user tries to launch an unsigned piece of malware, Gatekeeper will detect that it's not signed and display an alert. And as we can see on the slide, the only two options are move to trash or cancel. So Apple said, hey, we're not even going to allow the user to click OK and allow the item to run. So this, again, was a good step in the right direction. But as I mentioned, malware authors simply began signing their malware. And even though Gatekeeper would then check it, since they would be validly signed, they would be allowed to execute. So Apple said, okay, we need to raise the bar even more, and we need to introduce a technology that can hopefully prevent even signed malware from running. So in 2019, they introduced something known as notarization. And the idea is that in order for an application or executable code to run on a recent version of macOS, it has to be notarized. And what notarization is a mechanism where applications must be submitted to Apple and scanned and approved by Apple before they are allowed to run. So even if a hacker fraudulently obtains a code signing certificate or steals one and signs their malware, that now is not good enough. They now have to submit that binary to Apple, and the idea is Apple will detect that it contains malicious code and not notarize this. And this was actually a very strong security mechanism. We can see, for example, on the slide, hackers who slide into my DMs sometimes say, hey, look, like we're not able to get around notarization, and this is impacting our hacking operations because, generally speaking, Apple's not going to notarize malicious code. So that kind of gives us a good overview of the security mechanisms that are built into modern versions of macOS, specifically the ones that are designed to prevent users from inadvertently infecting themselves. And looking at these, it seems like they are all well and good, especially with the addition of notarization checks. A lot of Mac users and enterprise Mac users felt fairly secure and believe that, okay, maybe Apple's protection mechanisms were sufficient. But as we'll see, unfortunately, that was not the case. So the way I came across the bug was one of my friends, Cedric Owen, pinged me and said, hey, I basically built this application for a red team exercise. And when I deploy it, I don't see any of the expected alerts, right? There's no file quarantine alert, there's no gatekeeper alert, and there's no quarantine checks, even though the application I'm deploying is neither signed nor notarized, and yes, is from the internet. And as we can see on the slide, the little animated GIF I have here, you can see, yes, indeed, when I took his proof of concept and weaponized it into what appears to be a PDF document, on what was at the time a fully patched version of macOS, if the user would launch that item, none of Apple's security mechanisms seem to come into play, right? Where are all of the alerts? Where's Gatekeeper? Where's file quarantine? Where's notarization? So, we were both confused because it seemed like this bug or this application he had built somehow was bypassing all of these foundational security components. So he reached out to me to verify the bug and also to figure out the root cause. So now we're going to dive into triaging the vulnerability and ultimately figuring out where the flaw lay within the operating system. So we've talked a lot about the quarantine attribute and how it is a mechanism that triggers all these checks. So the first thing I wanted to do is make sure that this malicious or this interesting proof of concept application did have the quarantine attribute set. Maybe it was corrupted or something else. However, when I downloaded it from the internet, ran the xadder command, we can see, yes, indeed, it has the file quarantine attribute set. It's also not signed, meaning it's not notarized as well. So again, very perplexing because in theory, macOS should resoundingly block it. So what we have is an unsigned application that can bypass file quarantine, gatekeeper, and notarization requirements. And again, at the time, this was a fully patched version of macOS. So suffice to say, I was very intrigued and I wanted to figure out, what was the flaw, what's going on. So if we take a closer look at the proof of concept application, we find two very interesting aspects of it, which, as we will see, ultimately trigger the bug. So if you're familiar with applications on macOS, you might be familiar with the info.plist file. So applications are essentially a bundle or a directory that have certain files. And one common file is something known as an info.plist file. It's an XML document that has metadata about the application. Things like the path to its executable, what languages it supports, and this is a file I thought was required. Well, it turns out this proof of concept application did not have an info.plist file. Okay, that's interesting point number one. Number two, its main executable component was not a compiled binary, which is generally the case with applications on macOS, but was rather a POSIX shell script. So what we have, and I'll refer to this as a bare-boned application because it's missing an info.plist file, and since its component is a script versus a standard executable. And again, as I mentioned, those two characteristics of this application are ultimately why a flaw in macOS was triggered. So now I wanted to figure out what happened when I launched this application. Specifically, why weren't file quarantine, gatekeeper, and notarization checks being performed? Unfortunately, when you click an application on macOS, there are a myriad of components that all come into play. Let's say half a dozen, user mode daemons, frameworks, even the kernel that enforce different policies or check the application. So the flaw could lie in any of these components. So I didn't want to reverse engineer all of them. So I said, okay, what is a more efficient approach? So my idea was simply this. I was going to take 3 different applications, and I'll talk about the 3 different types, run them, and then simply look at the log messages that the system would print out to see if there was a divergence that would ultimately point me at least to the binary or the executable component where the flaw lay. So the 3 applications I chose, they are all unsigned, all from the internet, meaning they would all have a quarantine attribute, and in theory, file quarantine, gatekeeper, and notarization check should pop up and block them. The first application I used was a standard application, meaning it had an info.plist file, and its main executable component was a compiled binary. And as we can see, when we run this as expected, macOS basically says, hey, wait a minute, this is an unsigned application. I'm not going to allow it to run as expected. And we can see the alert, the pop-up on the screen. The second application I tried was similar to the first. Again, it had a standard application bundle with an info.plist file, but its main executable component was not a compiled executable, but rather a script. But again, macOS was like, I don't care. Even though you're trying to run this, this is unsigned. It's from the internet. I am not going to allow you to run, which again was expected. And then thirdly, we have the proof of concept application. This is the bare-boned application missing the info.plist file that also has a script-based executable component. And as we've mentioned, for some unknown reason, this is allowed to run without any prompts, any alerts. So what we're now going to do is we're going to look at the log messages from each of these applications, which will ultimately point us in the right direction. Before we do that, though, we need to talk about how to enable private logging on macOS. So in recent versions of macOS, Apple rightfully said, hey, a lot of sensitive information gets leaked into the logs. So what they actually do now is suppress things like file paths or other information, other log messages that may contain sensitive or private information. Obviously, in our analysis, though, we don't want these messages to be redacted. So we want them to be fully printed out. So what we need to do is tell the operating system, please log everything. Yes, we really know what we're doing. This is our system. Yes, I want to see, private messages, everything. And this is a good technique if you're reversing, other malware or other versions, or looking for other vulnerabilities in macOS. So the way you enable this is by installing what is known as a profile. And there's a link on the slide how to do this, but essentially it just instructs macOS to say, hey, please log everything for us. All right, so now we have private full logging enabled. Let's run the 3 applications and look for differences to hopefully figure out where the vulnerability lies. So first up, this is the standard application, has an info.plist file. Its executable component is a compiled mock-O binary. Again, this one was blocked as expected. If we run this and read through the log messages, first we note that a daemon called syspolicyd seems to be responsible for analyzing the application. It has a lot of log messages like, scanning the application, evaluating it. So this is good. We've kind of already pinpointed the daemon that's responsible for scanning the application. And as we'll eventually see, this indeed is where the vulnerability lies. If we continue to look at the log messages for this application, we can see a log message that refers to a gatekeeper evaluation. We can see the log message GK, gatekeeper, evaluation result. And then it prints out the results of the evaluation. We can see the evaluation type is 0. This is important, and we'll get to that in a second. Also, right below that, we can see a log message that says was allowed, :0, 0 meaning false or no, should prompt set to 1 or 0. And this is basically saying the operating system has decided that this application is invalid, shouldn't be allowed, and thus an alert should be shown to the user because it's unsigned, it's unnotarized. And again, this lines up with what we saw. This first application indeed was blocked and an alert was shown to the user. All right, what about the second application? Again, the second application was a pretty standard application, unsigned, had an info.plist file, but its executable component was a script, not a compiled binary. If we look at the log messages, they look very similar to the previous one, but there's one important difference. There is a log message at the top of the slide saying script evaluation. So this shows that there are at least two code paths in macOS for analyzing applications, one for applications that have standard compiled macOS binaries, and one that is for handling applications whose executable component is a script. So that's interesting. Again, though, if we look at the Gatekeeper evaluation results, they look identical to the previous application. We can see an evaluation result of 0 is returned, and then there's another log message right below that saying was allowed equals 0 or false. It's not allowed. And should show prompt is set to 1 or true. And again, this aligns with what we saw. This application was also blocked and a prompt was shown to the user. Finally, we have the barebone proof of concept application, which is allowed for some reason. If we look at the log messages, we can see they're fairly similar at the start. We see that script evaluation log message being displayed, which is not unexpected because, it is a script-based application. Interestingly enough, though, if we look at the Gatekeeper evaluation results, we see an evaluation result of type 2 is shown. Also, then, we don't see that was allowed should show prompt log message, which, again, kind of aligns to what we saw because no prompt was shown. We don't know why, but, it's missing in the logs, and that's kind of what we saw. So now we can summarize these three applications, right? The first two were blocked, and specifically when they were blocked, an evaluation result of type 0 was returned. Whereas for the proof of concept application that was allowed to execute, even though it was unsigned and non-notarized, it returned a evaluation type of 2. Interesting. So now the question becomes, what is evaluation type 2? Because it seems that if an application is evaluated with this type, it will be allowed to execute even though it's from the internet, unsigned, and non-notarized. So I set about reverse engineering syspolicy-d. Again, this is the daemon that was printing out all these log messages, so it seemed likely to be the one responsible for ultimately, evaluating the applications and setting this type. We find a method called evaluate scan result, and it, as one of its arguments, gets an evaluation type. And we can see in the disassembly or the decompilation of this system daemon that if the evaluation type is indeed set to 2, it specifically allows the application to be allowed and then returns allowing the application to execute. We can confirm this in a debugger if we set a breakpoint on this and look at various instance variables or properties about the evaluation object. And we can see that if we print out the allowed instance variable or property, it has been set to 1 or true or yes. And also, if we look at the would prompt flag, we can see that this is set to no. So again, this kind of just confirms that if an evaluation type of 2 is returned, the system will allow the application to execute with no other prompts or questions asked. So obviously we want to know why is this type 2 set, because for this proof of concept application, we think it shouldn't be, right? It's unsigned, it's from the internet, it should definitely be disallowed by the operating system. So if we continue to reverse engineer syspolicy-d, we can find a method called determine gatekeeper evaluation, and we can see various if-then code blocks within that. So let's kind of step through these, and we can do this in a debugger as well to confirm this. So first we see it calling a method is user approved. Since our application has not been user approved, we're going to fall into the next code check, which calls is script. Since our application does contain a script as its main executable component, this will evaluate to 2. So again, we continue into that code block. Interestingly enough, if we do that, the first thing we can see is that the evaluation type 2 is set into the R15 register, which ultimately gets returned. However, before that is returned, it calls a method that is named isBundled. And if isBundled returns false, this method will return with that evaluation type set to 2, which again means the application will be allowed. If we step through this in a debugger and we execute over the isBundled function call, this method, we can see that for our proof of concept application, the operating system has said, no, this is not a bundle. And that's weird because a bundle is kind of a macOS specific term that refers to applications. And we're an application, so we would expect for us to be classified as a bundle. So let's now dive into that to figure out why isBundle is not being set. So if we look at the method that's named isBundle, we see that just returns a flag, so that's not really very helpful. So what we need to do is go back and figure out where that flag was ultimately set. So we find that in a method called evaluate code for user, and I've highlighted that on the slide. You can see that it calls an unnamed subroutine, and the return value from that subroutine is passed to the set isBundled method call. So that flag is ultimately set by the return value of that unnamed subroutine. So we need to dig into that unnamed subroutine to figure out why our proof of concept application is not classified as a bundle. So if we look at the decompilation of this method, it should be very obvious exactly what is going on. We can see in the code it's simply looking for an info.plist file. Recall though, our proof of concept application does not have an info.plist file. Apparently this is not a required file to have in an application bundle. So what this means then is that this unnamed subroutine is essentially misclassifying our proof of concept application as not being a bundle, which means then that evaluation type 2 is ultimately returned, meaning that the application is allowed. So here let's briefly summarize that. If you have or had an application whose main executable component was a script that did not have an info.plist file, macOS would incorrectly classify that as not a bundle, meaning the evaluation type 2 would be returned, which ultimately means or meant that macOS would allow the application to run, skipping the Gatekeeper, Notarization, or file quarantine prompts. All right, so now we know what the flaw is, right? Basically a misclassification of bare bones script-based applications. Interesting. So I reached out to some friends and said, I have this really interesting vulnerability that was reported to me. I'm wondering if it has been exploited in the wild because it's a very powerful technique that would allow malicious adversaries to neatly sidestep all of macOS's recent security mechanisms and it'll really allow them to fall back to infecting macOS users in ways that they are very successful or were very successful in the past. So basically we said, okay, we know what the flaw is and we therefore can write a fairly comprehensive detection algorithm. Basically, we just want to look for applications that don't have an info.plist file whose executable is a script. Because again, these are the two components that would trigger the flaw and ultimately allow unsigned, non-notarized applications to run even on the latest version of macOS. So we did some searches. And honestly, I was not expecting to find anything. But turned out we actually found an application that conformed exactly to this necessary application bundle structure. So the application itself was named 1302.app. That in itself is kind of a red flag. It's kind of just some random numbers. And if we look at the directory structure, the files within the application bundle, we can see two things. A, it is missing an info.plist file, and B, its executable component is a script-based application. We can also confirm that though this application is from the internet, it is not signed. And if we do execute it on what was at the time a fully patched version of macOS, it was allowed to run. So this is problematic, right? This basically means attackers, adversaries, hackers, independently also discovered this vulnerability and were actively exploiting macOS users. I wanted to know, how users were being targeted with this. Turns out via poisoned search results on infected sites. So for example, if you Googled Alexa and Disney, the second search result would take you to a site that would have a pop-up saying that your Flash player needed to be updated. And if the user clicked on it, it would download an application that had been packaged in this way that would bypass all of macOS's security mechanisms. Yikes. So obviously this bug had been reported to Apple by Cedric, but since we had discovered that it was also being exploited in the wild, we said, okay, we need to figure out a way to provide a protection mechanism while Apple is working on a patch. So my idea was pretty straightforward, and it was, hey, can I simply detect and then block any downloaded code that is not notarized? I mean, this is what Apple is trying to do. Obviously, they messed it up, but the idea is still very solid. So now we're going to quickly walk through the 4 steps of how to implement this. First off, we need to detect anytime the user launches a new process. And we can do that by using Apple's Endpoint Security Framework, or the ESF. There's some sample code on the slide. Basically, though, you tell the operating system you're interested in process events, specifically the ES event type auth exec. Once you've registered for these events, the operating system will invoke your code, your tool, before the application is allowed to execute. The operating system will wait for you to say, yes, this is okay, or no, I should block it. Now we have a callback or an alert from the operating system every time the user executes or attempts to execute an application. We now need to determine if it's from the internet or not. Yes, we could check for that quarantine attribute, but we can also check to see if the application has been translocated. At translocation is a mechanism that Apple employed after a dilib hijack attack that I talked at DEF CON several years ago. And the idea is they copy it to a read-only share and launch it from that to protect against dilib injection attacks. What we can do is we can use a private API to query the application to see if it's been translocated. And if so, we know it's from the internet and the user is launching it. At this point, we want to do our final check to say, is that item notarized? Again, this is pretty straightforward. There are APIs that Apple provides that you can query an application to see if indeed it has been notarized or not. And if it hasn't, we simply return deny from that callback, the ESF callback, and then the operating system will prevent that application from running. So I wrapped this into one of my free open source security tools on Objective-C called Block. And we can see once it's been added, if we launch either the proof of concept application or the malware we discovered exploiting this vulnerability in the wild, even though Apple had not patched this flaw, we can very easily detect that this code is not notarized and then simply simply deny it, preventing it from being able to execute. We're now going to talk about detections because I also wanted to know, have I been exploited? Or, users could similarly answer this question, again, while awaiting Apple's patch. So I went back and I looked more at syspolicy-D, which again, recall is the daemon that is responsible for analyzing applications and ultimately where the flaw resided. And I noticed that it would always log the results of its evaluation, even the incorrect evaluation. And it did this to an undocumented database called the exec policy database. So what we can do is we can dump this database and we can see there are various events anytime the syspolicy daemon has performed an evaluation on an item that the user is running. Unfortunately, they don't specify the path, but just a file inode. But we can implement some interesting logic to, given a file node, recover the ultimate path. And so, we can now figure out the paths of the items and the policy results in this database. So I put together a simple Python script. This is open source if you want to dig into it. It basically parses the syspolicy database, that exec policy database, which again holds the results of any evaluations, even the incorrect evaluations. And from that pulls out all the paths and then checks if any of the items that were executed were a script-based application missing an info.plist file. So if we run this, we can see this on the slide after executing the malware in a virtual machine. Yes, indeed, this Python script is able to query the system and basically answer the question, hey, yes, a piece of malware had previously infected, or rather was allowed to execute on this system. So the last section of this talk before we wrap this up is briefly reverse engineering Apple's patch. So Apple patched this as CVE 2021 3657. I wanted to look at how they patch that because a lot of times Apple doesn't sufficiently provide a comprehensive patch. A lot of the CVEs I've received are by Apple incorrectly patching something. They won't patch the actual bug, just one code path, and if you can find another code path, that is another security flaw. So since I knew where the vulnerability lay, specifically within syspolicy I simply installed the update and then diffed the two binaries, the unpatched version and the patched version. Recall again, the vulnerability was in an unnamed subroutine that was misclassifying a bundle as not a bundle. So I simply looked for that new subroutine in the patched version. And if we look at various metadata about that, as we can see on the slide, we can see things like the size of that function was greatly increased, as were the code blocks, which indicates more checks were added. So I reverse engineered the new implementation of that unnamed subroutine and figured out that Apple had added additional checks to improve the isBundled algorithm. First, they check the item's path extension for app. This makes a lot of sense because for an application to launch, when the user double clicks it, it needs to be named .app. So now what they do is they just check the file extension, and if it ends in .app, they say, hey, this is a bundle, we don't need to do any checks. Good idea. The second thing they check for is if the bundle contains contents/macOS. These are required files, and this check also makes sense because you can have other type of bundles that aren't purely applications. So similar to the previous check, they basically look for this, and if the item they're checking conforms to this, they return yes, meaning the item is bundled. So to summarize the patch, if the item that is being launched either ends in .app or contains contents/macOS, the isBundled algorithm will now return yes, which means an evaluation type of 0, not 2, is returned, which ultimately then means that the operating system will block it and alert the user to this fact. We can confirm this by installing the patch, running the proof of concept application or the malware we found exploiting this, and see, yes, indeed, macOS now correctly identifies this item as a bundle and thus blocks it because it's from the internet, is unsigned, and is not notarized. So we're good, right? Well, turns out there was actually another interesting flaw that was very similarly related that has just been patched in macOS 12 Beta 6 and in macOS 11. Stay tuned. This is a very similar flaw, but in a completely different component of the operating system. All right, so let's wrap this up. Some conclusions. First and foremost, I really hope this illustrates that macOS has shallow bugs. This isn't to take any credit away from Cedric's discovery, but he essentially stumbled across this bug while playing around with application bundles. He didn't need an advanced fuzzer, but was able to craft an application that was able to sidestep all of macOS's recent security mechanisms, at least in the context of those protecting users from infecting themselves. So in this talk, we talked about the root cause analysis of the bug. We talked about how we were able to find it being exploited in the wild as a zero-day, and also how to implement some protections, detections, and how to analyze Apple's patch. One other takeaway for you all is that I really want you to also realize that many of the techniques we talked about today also apply to the analysis of other macOS vulnerabilities, operating system internals, or even reverse engineering macOS malware. And if you are interested in learning more specifically about Mac malware, I've written a free open source book on the topic. So just pop over to taomm.org and read The Art of Mac Malware Analysis. Finally, I want to shout out the companies and products who support me as an independent security researcher. Without their support, I wouldn't be able to find and analyze these bugs, and I wouldn't be here talking to you all today. So that is a wrap. These are the resources. Again, thank you so much for virtually attending my talk. I hope you're all staying safe, and I can't wait to see you in person at Ekoparty 2022. Aloha and mahalo.